Alright, in this video we look at another accumulation function problem, but specifically we focus on the derivative of this function called the derivative of the accumulation function. Okay, so let's take a look, write down some functions. We can see to the left of the screen we've got two functions. We've got a dotted line function, and that function is e to the negative x. Okay, and then there is the solid line function, which is the accumulation function, and it is the definite integral from 0 up to some number x of the function f of z dz. Z is used so that we don't repeat the x too many times. So here we're seeing that f of z is equal to e to the negative z. Okay. So if we would actually like to find this accumulation function, we're going to do the definite integral from 0 to x of e to the negative z dz. Okay? And that accumulation function is going to require us to find an antiderivative of the given function. We need to find the antiderivative of e to the negative z, and then we need to evaluate from 0 to x. Okay? And what we're going to find is that the accumulation function is just another function. It's a new function. It's another or a new function. Okay? And because of the particular function e to the negative x that we've chosen, we can actually find what this accumulation function is. So we'll find that the antiderivative of e to the negative z has to be an e to the negative z. Okay, but it's not quite correct because we're going to need a plus or a minus sign. Okay, because when you take the derivative, we're supposed to get e to the negative z. And when you take the derivative of e to the negative z, which is what we thought our antiderivative was going to be, we find from the chain rule that you get a negative from the derivative of the inside function negative z. Okay, so we can see that we don't quite have the right antiderivative, but if we put a minus sign here, okay, then the derivative of negative e to the negative z is positive e to the negative z, which says that our antiderivative is negative e to the negative z. Okay, so we've done the antiderivative problem, then we need to evaluate from 0 to x, which is equal to negative e to the negative x minus negative e to the negative 0. And because e to the 0 is equal to 1, negative negative 1 makes a positive 1, we can see that the area function is 1 minus e to the negative x. There is our area function. Okay, so let's look and see about if this answer makes sense. We had the function dotted line given, and we now have a solid line function given as the area function as the solid line. So let's look and see what happens as x gets bigger and bigger and bigger. Right? We're seeing that the dotted line is e to the negative x. We're adding up area, so the area is getting smaller and smaller, but the total amount of area keeps getting bigger and bigger and bigger. We're just happen to be adding up less and less areas. Right? The amount of area that we're adding is getting smaller, but we keep adding up these smaller amounts, so the area keeps going bigger and bigger and bigger. Okay. And if we take a look at this problem, look at the area function, which is the solid line there, we can look at what happens as x goes to infinity of this area function. And because of the e to the negative x in this problem, e to the negative x goes to 0 as x goes to infinity. So we can see here that the area is going to keep climbing and getting closer and closer to 1, which is the limit. Okay, but the bigger we make x, right, we're going to keep getting more and more area, but that blue line is never going to go above 1 because 1 is the maximum amount of area we can have. Okay, So there is our area function and an explanation of why the area function seems to be making sense, that our area is climbing, getting bigger and bigger, but because we're adding less and less area, the area we're adding gets smaller and smaller, that eventually this area function, accumulation function, limits to 1. Okay. So one thing that's going to be interesting to note here is that because the area function is actually a function, it's possible to take the derivative of that function. What is the derivative of the accumulation function? Well, because we have an actual formula for it, we can take the derivative of that function. The derivative of 1 is equal to 0. The derivative of negative e to the negative x is negative e to the negative x. We had a chain rule problem. Positive, negative makes a positive, so the derivative of our area function comes out to be e to the negative x, which is the original function itself. Okay. So what we're seeing in this example is a special case of something called the fundamental theorem of calculus part 1, that if you have a function f of x that is given to you, okay, and we make an accumulation function, which is the definite integral from 0 to x of f of z dz, right, that this will be a new function that we can then try to take the derivative of. If you take the derivative of this accumulation function, what you'll find is that you get f of x, the original function we started with. So the way to write that, an alternate way of writing this, is called the fundamental theorem of calculus part 1. That if you take the derivative of an accumulation function, which is the integral from 0 to x, of some function f of z dz, okay, that the answer you will get is the function evaluated at x. The function you are integrating becomes, once you take the derivative of the integral of that function, you get that function back again. Okay, so that is one way of saying it, or slightly more general, we can say that the derivative of the definite integral from any number, not necessarily 0, but from any number up to x, f of z dz, is equal to f of x. So even though that there is a value a here, we are still going to get the original function f of x. And as an example there, we might take a look at the function f of x is again equal to e to the negative x. And then if we look at the accumulation function, let's say find the definite integral from 1, so a is equal to 1 instead of 0, up to x, e to the negative z dz. So here's the accumulation function from a value of 1. Okay, so we're finding the area from 1 up to some number x. Okay, and that value of x can change. Okay, so let's see what happens as x gets bigger and bigger and bigger. Okay, what do we think is going to happen? Does this thing level out? It does in fact level out, but we need to figure out what that number is. Okay, so let's find this accumulation function. The antiderivative of the inside function, e to the negative z, and then we need to evaluate from x to 1. So that would be negative e to the negative z, there's the antiderivative from 1 to x. Okay, and we'll get negative e to the negative x minus e to the negative minus a minus, which is a positive e to the negative 1. So the accumulation function is equal to e to the negative 1 minus e to the negative x. And therefore, when you take the limit as x goes to infinity of this accumulation function, you get e to the negative 1, which is 1 over e. And 1 over e, we can see, according to 1 over e to the 1, let's convert that to a decimal, 0.3678. So that's where that blue line is leveling out at 1 over e. Okay? All right, now the question is, what is the derivative of this accumulation function? The derivative with respect to x of a of x, even though there is a number here, not 0 on the bottom, the derivative of this accumulation function, because 1 over e is a constant, that derivative becomes 0, and then we get e to the negative x, which is the derivative of negative e to the negative x. So the derivative of the accumulation function is still the function on the inside evaluated at x, even though there is a constant. Okay? So in the next video, we'll look at other types of interesting functions that can appear from accumulation functions.